These next few videos are meant to be a review on things that you should already know, particularly about math and chemistry. It's important that you're able to do this stuff quickly. At the beginning of the semester, we kind of focus in a little bit on review, right? So we'll be talking about some math, we'll be talking about matter, we'll be talking about reactions. But after that, then we start to get into a lot of theory. We start to get into some very heavy topics that require you to be able to just do the math already. So it's important for you to understand where you are in terms of the math and the naming, right? The stuff that was in the previous videos. If you are lacking, you need to take it upon yourself to step it up and look for extra resources or come see me during office hours, etc. Because you will fall behind very rapidly if this stuff isn't almost second nature to you. So practice, then come talk to me. So in measurements in chemistry are important. Measurements are basically how we gather our empirical data. There's different types of measurements, right? We have length, which is a measurement of distance. The unit that we use most often is the meter or some other form of this with a prefix. Volume is the amount of space something takes up. The base unit for this is liters. Mass is the amount of stuff or matter in something. Gram is the usual for this one. Weight is a gravitational effect. So for example, they say, oh, if you weigh yourself on the moon, you weigh less compared to here. That's true, but your your mass would still be the same. So you need to be able to identify what type of a unit and what type of measurement is being done. So if I say milligrams, you should immediately say that this is a mass unit or a weight, depending. We'll be using that kind of interchangeably, even though they're not the same thing. If I say a nanoliter, you should be like, oh yeah, that's a volume. Okay, because you are allowed to convert from milligrams to grams very easily using prefixes, but you are not allowed to convert from milligrams to milliliters without a special unit, most likely density. Okay, you can't just automatically go to that. So I know this says base units. That's not exactly correct. SI base quantities are the ones that are kind of the standard. You notice that it doesn't match with the base units for the metric system. That's fine. It's just the most common units that are used. They're the ones that are considered the standard, right? Time is usually given in seconds. Temperature is in Kelvin, and we'll talk about why that is in gas law. The amount of substance is a mole. Current is amps, and luminosity is candela, which there's other units for too, which is just basically the brightness of something. So these are just kind of the SI units that you'll see throughout, but it doesn't mean that they're the only units, and it doesn't mean that it's the units that we're going to use kind of as a middle ground. So speaking of the middle ground, the metric system. So I served in the military for 8 years. I love my country. This country is stupid though when it comes to units of measurement. So if you think about inches in a foot, there's 12 inches in a foot, there's 3 feet in a yard, there's 5,280 feet in a mile. That's stupid. Compared to the metric system, there's 10 centimeters in a meter, there's 1,000 millimeters in a meter. It's a nice base 10 unit. So what we do is we take, in order to scale up and down, because saying that I'm going to drive to work and it's going to be 40,000 meters, That's a lot. Instead, what we do is we kind of scale things up and scale things down using prefixes. The way that we do that is we use a base unit. For length, it's a meter. For mass, it's a gram. For volume, it's a liter. And for time, it's a second. And what we do is in order to scale something up, we use these prefixes. Okay. Now, in terms of the ones that you have to know, it's on your memorization sheet. If I remember correctly, it's in between giga and femto. The major ones that we use are going to be in between kilo and pico. Okay. Those are the major ones. So, like if we say there's 1,000 centimeters, or excuse me, 100 centimeters, I can convert this into 1 meter. Okay. If I have 10 to the 9 nanometers, I can convert this over to 1 meter as well. Now, there's a couple of different ways to use this chart. I use dimensional analysis, and I use a dimensional analysis grid. So I like non-fraction or non-negative numbers in my exponents. Okay. So there's a couple of different ways to use this. For me, what I do is I always use, well, that's huge. I don't need it that big. I always use positive exponents. So I would say that if I have 10 meters, for every 1 meter, I have 10 to the 2 centimeters. Okay, which is 100 centimeters. Oops, this is meters. The way that this chart is set up over here is that these are the numbers that will always be applied to the base unit. So for example, if I do this system, 10 meters. I look at my centimeter I want to convert to. I would say I have 10 to the negative 2 meters for every 1 centimeter. So this is basically the amount of base unit per 1 of the new unit. So in other words, there are 10 to the negative 9 meters in 1 nanometer. So that's the way that chart works. There's several derived units that we're going to be talking about. Area, okay, and these are just kind of the base equations. You're going to need to use this for some algebra. Area is just the sides times each other, right? Which ends up becoming that. Volume then takes the next step and says, okay, I'm going to add another dimension to A, and this becomes, like, could be this, or if this is different, it would just be A times L or A times X. Or, if we really want to break it out, length times width times height, which I did that not in the order I said it. Speed is a unit of distance per time. Force is the rate of change of momentum, which we're going to kind of play with a little bit. We can kind of think this is in terms of mass times acceleration. The unit that we use for this, by the way, is the Newton. Pressure is a force exerted over a given area. Energy is the essentially the ability to do work. The unit that we use for this is the joule. So the conversion is actually Newton meters is a joule. So the amount of force to move a given amount of distance. And then density is a mass over volume. We'll be using this one quite a bit to begin with, and throughout the semester. The last thing I'm going to talk about in this video is sig figs. So sig figs are important in terms of measurements because basically you can think of it like this. The more sig figs there are, the more expensive the instrument is. So we want to be able to report the correct values based on our findings, right? If I used a ruler to measure, the diameter of a sphere, like a little ball bearing or something, I wouldn't report that out as 1.000 centimeters. That's not accurate because I can't get that kind of a measurement with a ruler. I could with a pair of calipers, not with a ruler. So the rules for significant digits go like this. The first thing you should do, and I'll put this as kind of like A instead of 1, is look for a decimal. Because this is going to affect a lot of things. Non-zero digits that are listed or that are measured, I guess would be the best way to say it, are significant. Trap zeros are significant. What does that mean? If I have 101, this has 3 sig figs. Sorry, let me fix that real quick. 3 SF. Leading zeros are zeros before the number. So like 0.0001, right, are not sig figs. They're just basically to tell us the scale, right? Like where are we at on things. Trailing zeros. This is These are zeros. I spelled zeros wrong up there. Let me fix that. Sorry. And trailing zeros are basically zeros after sig fig. So something like 100. This is where the decimal is important. If there is a decimal, they are sig figs. If there's no decimal, they aren't. So for example, if I ask you 100 like this and 100 like this, how many sig figs does each one have? This is 1 sig fig because it doesn't have the decimal. This is 3 sig figs. Now, when you add and subtract these different numbers, or you multiply and divide, there's different rules for each one. So before I talk about those rules, the one thing I do want to mention is rounding. Do not round until the very end, okay? You get rounding errors if you just keep every single time that you write. So my general thing is if you have to rewrite the number, I always keep the numbers in my calculator and just work from there. But if you have to rewrite a number, so let's say you have 0.761256 on your calculator, 9 there. And this is my last sig fig. The way that I do this is I underline my last sig fig. And then if I have to rewrite this into another part of the problem, I always take at least the next digit after that. Okay? This will eliminate most of the rounding errors, but it's better to take a couple more if you can. Okay, but I understand everybody's crunched for time, right? You don't want to write out a million digits. When it comes to rounding, we don't round until we get a final answer. If we have the number next to, so these are the numbers next to on the right of the number we will round. This is round down. round up, round even. That's weird, right? So basically it goes like this. If I have 1.1 and I have a 5 here, and this is my last sig fig, I could either go up to 1.2 or I could go down to 1.1. 2 is even, we would round that way. If this number was 1.85, this is my last sig fig, and I need to round, I could either round up to 1.9 or I could round down to 1.8. I'd round down to 1.8. When it comes to addition subtraction rules for sig figs, it's all about the least precise number. So you can't report any numbers past the least precise measurement. So if I have something like 1.00002 milligrams plus, and I'm going to add this to a really crappy scale at 2.1 milligrams. If my final digit, because this is my least precise. The least precise one is the one that goes the least to the right. This answer is 3.1 milligrams. This doesn't matter. It's like adding a dropper, right, or a pipette to a pool, right, like a swimming pool. It doesn't have an impact on it. For multiplication and division, the number of sig figs reported must match the count of the number with the lowest sig figs. So in other words, if I have 3.26 times 1.0, right? I know it's just going to be 3.26 again. This has 3 sig figs. This has 2 sig figs. My number then becomes 3.3. Why? Because this has 2 sig figs. So you got to be able to count your sig figs. And in the end, you only report the amount of sig figs that matches with the one that has the lowest amount. Counted numbers have infinite sig figs. So in other words, if I have one apple, I know it's 1.0000000 apples. And then conversions. It's as long as, so it's all, I guess this would say, let me put it like this. Metric conversions are infinite sig figs. Now, this is where scientific notation comes in. If you don't know scientific notation, you gotta get good at that because we use it a ton in chemistry. When we report a number, this has 2 sig figs. And this is the way that becomes easier let's say I have to write 1200, right? So that's 1, 2, 3. Yeah, okay. So 1200, right? And I don't want to write it like this because I'm like, oh, I don't want to have those 2 zeros. This is how I write it as a scientific notation. Now, let's say I had this. This now has 4 sig figs, right? Both of these zeros are significant. So if I wanted to write it in scientific notation, this would be 1.200 times 10 to the third. So we can see our scientific notation helps us with sig figs. And this is the easier way to write it. Like, let's say I had 1010. This is significant, right? So instead of writing it like this, I can do like that. And it helps me to see who's significant, who's not.